Now we're going to begin section 5.2, which is the section on sequences and convergence. So let's start by defining a sequence. So let's let X be let's say just a set. In most of this section, we'll be thinking about metric spaces, but let's start by just having sequences in sets. So let's suppose for each natural number n, there is a point xn in X. Then we call xn a sequence. In X. And this is very much like sequences of real numbers back in section 1.3. A sequence you can think of as a function from the natural numbers to the set X. But instead of saying X of n, we say X sub n. And so that's a sequence. And now let's write down the old definition of Cauchy's sequence of real numbers. This is definition 1.3.12. A sequence of real numbers, we call that is a Cauchy sequence. If for every positive number epsilon, there is a natural number n, such that if little m and little n are both greater than or equal to big N, then the absolute value of xn minus xm is less than epsilon. And we can change this definition. We can tweak it a little bit to define a Cauchy sequence in a metric space. So let's go ahead and make our changes. This is now definition 5.2.3. So we're going to let XD be a metric space. And then instead of a sequence of points in the real numbers, this is a sequence of points in our metric space X. And then instead of taking the absolute value of the difference, remember that's just the distance in the real numbers, we're going to take the distance in our metric space. So Cauchy sequence in a metric space is just pretty much exactly like a Cauchy sequence in the real numbers with exactly the changes you'd expect. And we can define a convergence sequence pretty similarly. Now you may remember from section 1.3 that a convergence sequence in the real numbers is defined in terms of open intervals. And there's a branch of mathematics called point set topology that generalizes open intervals and uses that to define convergent sequences. But we're doing metric spaces, which is a little bit of a different approach. So it turns out that what we can generalize is proposition 1.3.3. So we're going to let XD be a metric space. And we're going to pick a sequence of points in our metric space and a single target points in our metric space. We say the sequence converges to X. And we use all the usual notation for that at xn goes to x, or limit of n xn equals x. If, and then we use the epsilon definition for all positive numbers epsilon. There is a positive number n, in fact a natural number n, such that if little n is bigger than big N, and as usual in analysis, we don't bother to write down the implied hypothesis that little n is a natural number, then now no absolute values, the distance from xn to x is less than epsilon. Let's draw a Cauchy sequence in two-dimensional Euclidean space. It's going to be two-dimensional Euclidean space because that's the number of dimensions of this video. So here's our first point, here's our second point, here's our third point, fourth point, fifth, sixth, seventh, eighth, ninth. And then we see as we go on, our points are getting closer and closer together. And so that's what it means to be a Cauchy sequence. And in this case, we can see they're converging to some target point X. I'm going to give you 3 examples of metric spaces where we can relate being Cauchy or being convergent to something we already know. The first one is the discrete metric. Your book calls this example 5.2.2c and 5.2.4c, but I think it's really a proposition. Let's let X be a set, and we're going to let the discrete metric, let me remind you what this is, that says the distance from the point X to the point Y, that's 0 if they are the same point, and 1 if they are not the same point. And let's let Xn be a sequence of points in X. Then the following statements are equivalent. And so the following 3 things, if any one of them is true, the other 2 are true. If any one of them is false, the other is false. The first equivalent statement is that Xn is a Cauchy sequence. And the second is that Xn is convergent. And we recall all that that means. There is a point x in x such that xn converges to x. And the third equivalent condition is that our sequence is eventually constant. And what that means is that there exists a natural number n such that if little n is bigger than big N, and also a point x in x such that if little n is greater than or equal to n, then xn is equal to x. So there is some point in our space, our metric space, and some point in the sequence such that after it, your sequence is just x, 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 the same point over and over and over. So let's prove this. Actually, I'm only going to prove two of the directions because some of the directions are obvious. So clearly, if C is true, then A and B are true. And you can check that by just, no matter what your epsilon is in your definition of Cauchy or your definition of convergence, you pick big N being this big N in the definition of eventually constant. And then past that point, you're always a distance 0 from the target point x, which means you're a distance 0 from the other points in the sequence. And so if you're eventually constant, then you converge to the thing you're eventually constant at. And if you're you're a convergent sequence, so you're Cauchy. And in fact, that C implies A and B, that's true not only in the discrete case, that's true for all metric spaces. It's the reverse implication that's only true in the discrete case, and that's also interesting. So now let's prove the reverse implication that both A and B imply C. If they imply C, they'll imply each other. And I'm going to go ahead and prove these two things all in one go. Suppose A or B is true. And we're going to let epsilon be the number 1/2. You can pick any number that's positive unless and 1 in this argument will work. But 1/2 is just kind of convenient. So if A is true, if the sequence is Cauchy, let capital N be such that if little n and little m are both greater than or equal to capital N, then the distance from xn to xm is less than epsilon, also known as 1/2. And in this case, we're going to define little x to be little x sub big N. And that capital N exists is just the definition of Cauchy. And if B is true, let N be such that if little n is bigger than big N, then the distance from xn to x. Remember, it's convergence, and x is what it converges to. That's less than epsilon, also known as 1/2. So in either case, we found a number big N such that if little n is bigger than big N, then the distance from xn to x is less than 1/2. But in the convergent case, it's definition of convergence. In the Cauchy case, it's big N is indeed greater than or equal to big N, so every point after that has to be within epsilon of xn, which is what we called x. And now we use the fact that this is the discrete metric. Distance from xn to x is either 0 or 1. So the distance from xn to x has to be 0. It can't be 1, so it must be 0. So by definition of the discrete metric, xn equals x for all little n bigger than or equal to big N, and that is exactly our condition C. So C is true. And that completes the proof. So for the discrete metric, Cauchy and convergent both mean eventually constant, which isn't a topic we've talked about much, but is simple enough that you all understand it. Now we're going to talk a little bit more about convergence in our in Euclidean space under the usual Pythagorean metric that we all know and love. And this is example 5.2.2b, and also homework problem exercise 5.2.3. I won't do the bits of it that are exercise 5.2.3, but because I'll leave those as an exam problem, but I will at least state it. So let's let our set X be Euclidean space. So P dimensions, and we're going to use the usual metrics, the distance from the point X to the point Y is the sum. You take the sum starting from k equals 1 up to p. You take the kth coordinate of x, you subtract off the kth coordinate of y, you take the distance between those two numbers, and you square it. Since you're squaring it, it doesn't matter if you put absolute values or not. You sum those up, and you take the square root. And let's let xn, this is a sequence of points in our Euclidean space. And let's pick one target point in Euclidean space. And then here is the two parts, the convergence part, which I will prove, and the Cauchy part, which I'll leave as homework. Xn converges to x if and only if you grab the coordinate functions. The coordinates converge for each number between 1 and the number of dimensions. And the second part, the Cauchy part, this is Cauchy. if and only if the sequences of coordinates is Cauchy for each dimension. Before I prove that, I want to say a little bit about notation. Now, you are probably used to writing points in 2 dimensions with x and y coordinates. So you are used to this. And points in R3 and then if you need to refer to a particular point, you just call it XY or you call it XYZ. And maybe if you had 4 dimensions, you might call them X, Y, Z, W, but if you've got P dimensions, what can you do? You don't want to say X, Y, Z, W, A, B. I don't know how many letters. There's P letters. So what we do, and what you're probably going to do from now on, is you call your points your coordinates are X1, X2, X3, up to XP, or sometimes you write the coordinates as superscripts. And that is probably what we are going to do. So we do not use this notation anymore, or the coordinates are usually going to be X1, X2, and X1, X2, X3. There are some exceptions. There are some cases where we're going to call them XY and XZ again, but in this particular problem statement, we're going to call them X1, X2 up through XP. And one benefit of doing it this way is that not only does it work for as many coordinates as you want, but you can also, there's also this very natural, very simple name for just the whole collection of them. If you don't feel like writing X1, X2, X3, comma, dot, 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 comma, XP, you just write X. And that can be very helpful. Now, everybody wants to use subscripts because everybody sees a superscript and just thinks, oh, power x2. They think that means x squared, or not x number 2. But sometimes we need both subscripts and superscripts because we're talking about 2 different things. So sequences in RP. We want to write a sequence as x sub n, where x sub n is the point with coordinates xn1, xn2, up through x in the pth coordinate. And now we need 2 numbers. They can't both be the subscript, so we're going to make the coordinate number the superscript. In chapter 5 of this book, we care a lot more about xn as the nth point in a sequence than xn as the nth coordinate. So we're going to let the subscript be the point in the sequence and the superscript be the coordinate. So let's prove part A. Now that I've told you what all the things in the theorem statement actually mean. So let's suppose that xn is converging to x. Then we pick epsilon bigger than 0, and let n be a natural number such that if you're bigger than n, then the distance from xn to x is less than epsilon. But let's write out what that distance is. It's the sum from k equals 1 to p, xn, the kth coordinate of that, minus x, the kth coordinate. You square it and take it to the 1/2. And notice that since you're adding up a bunch of squares and we're in the real numbers, you're adding up a bunch of non-negative things. So if you fix any particular j, this is bigger than or equal to x, the eighth one of these, also known as the distance in R. And this is true for each j between 1 and n. So for every epsilon, there is a big N such that if little n is bigger than big N, then the distance from xnj to xj is less than epsilon. So that is exactly the definition of xnj converges to xj. Or actually, let me write this as a limit notation so I can remind us that it's the variable n that is going to infinity, not the variable j. And let's take the converse. Let's suppose that the limit of the xnj's or the xnk's is xk for each k between 1 and p. Let's let nk be such that if we're bigger than nk, then by convergence in the real numbers, you're less than, in this case, let's go ahead and take epsilon and divide it by the square root of p. And then we're going to let big N be the maximum of R. Of our p numbers, and since there's finitely many of them, that's a finite natural number. And then if little n is bigger than big N, then the distance from xn to x we write as our sum. And then since little n is bigger than big N, it's bigger than nk. So the thing in the inside, the thing inside the absolute values, that's less than epsilon over the square root of p, whole thing squared, then 1/2. And then now notice we're summing something that doesn't depend on k. So we've just got p terms that are each of size epsilon squared over p. 1/2 is just epsilon. So the conclusion is that xn converges to x. One other proposition that I want to state that your book This is an example, and that I am not going to prove because it is a study problem. So we're going to start with a metric space. And we're going to grab a sequence in this metric space. And a target point in the metric space. And then the conclusion is that if your points are converging, if they're getting closer and closer to X, then the sequence is Cauchy. And this is a very straightforward application of the triangle inequality. And you will probably prove this on exam 1. But I wanted to state it to motivate the next definition. This is, so here we've got a metric space. And we say, if we've got the converse to this proposition, if whenever you've got a sequence of points in your metric space is Cauchy, if every Cauchy sequence is convergent, that is, whenever it's convergent, there exists a point X that it converges to, then we say X is complete. Couple of examples of complete metric spaces. So we saw that under the discrete metric, so if we saw before that Cauchy sequences are sequences that are eventually constant, and convergent sequences are also sequences that are eventually constant. So the discrete metric spaces are always complete. For example, from last semester, is that by theorem 1.3.13, the metric space R, where the distance is just absolute value of X minus Y, R is complete. And classic example, the rationals is not complete. And so let's consider this sequence. 3 is rational, 3.1 is rational, 3.14 is rational, 3.141 is rational. This is a sequence of rational numbers, but it's not converging to a rational number. It's trying to converge to pi. But pi is a real number, not a rational, and if you think of it as a sequence of real numbers, it can't converge to two things, so it cannot converge to a rational. Another possible exam problem is to show that Euclidean space in more than one dimensions is also complete. That's exercise 5.2.3. So here is a proposition from section 1.3. So the version in section 1.3 looks like the following. Let's say you've got a sequence of points contained in the real numbers and a point A that is a real number and a subsequence and then if AN converges to A, if the whole sequence converges to A, then the subsequence also converges, and it converges to the same point. And we can modify this to be to the case of metric spaces. We let XD be a metric space. And if you've got a sequence in your metric space and a point in your metric space, then any subsequence converges, and exactly the same proof works as in section 1.3, so we will not write that out. And conversely, it's not at all hard to come up with examples of sequences that have convergent subsequences, but themselves do not converge. But you can't come up with an example like that that's Cauchy. So here is proposition 5.2.5. So we start in a metric space. Doesn't have to be complete, I should mention. And we're going to take a subsequence, a sequence of points that are Cauchy, and we'll grab a subsequence. And let's name our target point. And then the conclusion is that if the subsequence converges to our target point, then the full sequence converges to our target point. And let's prove this. It'll be an epsilon n proof. You pick an epsilon greater than 0, and let's let k be a natural number such that we'll use the definition of convergence. If little k is bigger than big K, then xnk, it's only our subsequence that converges, so we need xnk, and let's make that less than epsilon over 2. We'll probably need another epsilon over 2. And let's let n1 be the natural number in the definition of Cauchy sequence. So if n and m are bigger than n1, then xn minus xm that one, we'll also let that be less than epsilon over 2. And then we're going to let capital N be whichever is bigger, our N1 or our K. We're already using N sort of for the indices of the subsequence, so we're going to use some different letter. We're going to suppose little m is bigger than or equal to our capital N. And then notice that n sub m is at least m. N1 has to be a natural number. It has to be at least 1. N2 is bigger than N1, so it's got to be at least 1 more than N1, so it's got to be at least 2. It's a straightforward induction argument. We did it implicitly at some point last semester, so we'll stipulate that everyone knows it by now. So then we do some algebra. The distance oh my, I've made a mistake up here. I've used absolute values. So, and I should not do that. I need to use, we're in a metric space. We aren't using absolute values. We're using distances. So I need to make these D's. Yes, please don't make this mistake on your homework. So then the distance from x sub m to x, triangle inequality, distance from xm to xn sub m, which is in the subsequence, plus the distance from x sub n sub m to x. This is less than, let's keep the first piece in place, n sub m plus epsilon over 2, because m is bigger than big N, which is at least k. And that is less than epsilon over 2 plus epsilon over 2, and that's because m and n sub m are at least big N, which is at least big N sub 1, the number from the definition of Cauchy sequence. So if m is bigger than big N, then the distance from xm to x is less than epsilon. So the limit of the xm's is x. The sequence proper is converging to x. That completes the proof.